scale, they have both the characteristics. So we call them as dual characteristics. So they are not, you can't always classify them that, oh, these are all only particle. So how is this coming? These are like detailed science and we don't have to go into detail. That makes things fundamentally different. So for which I know Einstein and many of them actually got Nobel Prize for it. So you might recall that how atomic structure looks like. There's a nucleus and there are electrons. When electrons go from one point to the other one, you can actually get just one photon coming out. So the light would be billions of them, this light, but it's one by one is making them a billion. So this is something which the idea of particle and wave nature together makes it quantum mechanical, and that's what we are going to leverage for developing technology. So there were last year we celebrated, the whole world celebrated 100 years of quantum mechanics because it kind of gave a good understanding of how atoms and other things behave, like a subatomic particle, what we call behave at behave and how we can model them. So this was in 1922 and 26. After that, it has been a good. So there is a simple experiment. So why I am giving this simple experiment is if somebody has to build a technology, you need to know little bit of basics. Only then you can start building technology and look at innovation. So when I have a slit, right, or like if you say somebody might have seen dams. When you have dam, you have gates opening of the dam when the water falls. Water is sent out. Now when the water is coming out, if there are multiple gates open, the water interferes and then you end up having waves. So there is the wave behavior. Now whether to understand light is wave or a particle, what we do, there's some small experiments which we can, there's a double slit experiment what we call, you might have done it in your school, but that's with the light. So if one of the slit is open and you end up seeing particle at only one slide, or a light just gets intensity at one point. So now if I have two of them, this is what should happen. If they are particle, if they are just coming as one after other as a particle, I should end up getting this pattern. But what generally happens when people do experiment is you end up getting them as a wave. So which means the light, if I'm just looking at one slit, it looks like a particle, but then the moment you have two of them, then it means that they are behaving like a wave and then you are having an interference. So now this is something which people mastered for many years and they've tried to understand and look at it. Now I have another way of looking at the same problem. If I can I have, it's a mirror, right? A mirror, what it does, it translates something and it also reflects some part of it. So I can think of a mirror which has a 50-50 like transmission and or what we call as a beam splitter. 50% of the time it reflects and 50% it translates. I end up having a 50-50 interference pattern. I mean a 50-50 probability of finding them. Now what people try to do is that can I split light? Can I make them into two parts? What we call as splitting of photon. Is splitting of photon possible? But when they did this experiment n number of times, they could not get a single photon getting split into two. At any given time, there was a detection at only D1 or D2. These are detectors. But if I'm doing it 10,000 times, I will get 5,000 here. But at any given time, there will be only one detector which clicks. What it says is that they are not something which you can split. Then how are they going in the previous experiment, previous setup I showed here, right? If the light is going here, only photon splits. It can go in two paths and you can have an interference. But what the next experiment shows is that you are not seeing the splitting, but still, how did we get the interference? So that is where the fundamental question came into. And then they said, okay, photons don't split, but something much more strange is happening, the way they try to understand. So what it says is that they are like waves, they are not splitting, they are going together in both the path, and then they are interfering. So the light is going together in both the paths. It's just like the waves, amplitude splits, and then you end up getting like, there's a light at both the paths, a single photon is at both the places, and then they interfere and they again interfere. And then when two waves are there, you can have an amplitude going high, we can constructive interference, and we can have destructive interference. So those things happen, and you can actually control whether you have high probability here and low probability of finding a particle here just by controlling the way the interference happen at these two paths. In fact, these are like slightly technical detail, but why I'm giving you all these things is, you might find it a bit strange. Now, before going into the detail, I'll just ask you one more question. You are all do computing, right? How is our computers working? How do computers work? What is the input you give? We all have binaries, you agree, right? It's all zeros and ones. There's nothing more. I have a big complicated problem. When you write a program and you define a problem, it is converted into a sequence of zeros and ones, and those zeros and ones goes into a system, and then it does an operation, you get back, and that is your solution, right? Now, zeros and ones are the binaries which define our computational task. So you can say I can do 2 into 2 is 4. I can easily calculate them by hand and I look at it. But if I ask computer to do 2 into 2, it converts 2 to a binary and another 2 into a binary, and even multiplication sign is converted to an operation some form and you get an output. Now, why I'm getting into this point is that is for quantum computing, we need to find an equivalent of the zeros and ones. If I have to use atoms to do computers or do photons, I have to do zeros and ones. So this is something which we can take a look at it. I'll just this and I can say how I can look at computing. Right? Computing, when we said there is some input and there will be some dynamics, that's what zeros and ones operations which happens, and then you get an output as a result. Now, instead of doing it in a classical computer, can I use a quantum system which does such kind of operation? Can it do better? And that's how we are trying to ask a question, right? So I will say what makes the difference here, right? So I will. This is a simple example of what I said. I have a single photon. It can be in superposition, which is not like a classical particle which is going. And can I treat this as a small computer and then build a big one over a period of time? So this captures the difference between quantum and the classical computer or any devices. So you all said zeros and ones. The binaries is there, is what the way we do compute. But if I take an atom, or if I take a photon, or if I take an electron, you all have heard of electrons as spin up and spin down. Photons have polarization, right? Horizontal, vertical polarization. So atoms can be in ground state and excited state. So, and it can also be in superposition, what we call, because I told, if I have a beam splitter, when the light is going, it is at both the place at the output. It's not at just one point. No, that's what this quantum mechanical systems does at a very small scale. So when I look at an atom, there's a ground state and excited state. There is a spontaneous oscillation that you will never be able to say whether it's a ground or excited state. We call them a superposition state. At any given time, it can be in the superposition of both of them. Now that is at the atomic scale. Now what difference that is that giving is you can have a state which can be in simultaneously at both of them, which does not happen with the classical computer or a classical binary language. It's either 0 or 1. But in a quantum system, it can be in 0 and 1 simultaneously, and that makes a big difference. For example, if I have a coin, I toss a coin. What will I do? What will I get? Head or tail? Right? If I get head, I decide I will move to the right. If I get tail, I will decide I will move to the left. So if I do like this, I toss a coin. So now head and tail can be treated as 0 or 1 in a classical computer, and then you end up going to some particular point. So you all use your Google search today, or ChatGPT goes and gets some information for you, right? How are they getting? It is searching somewhere. Your command is going and it is searching and then it is giving you back. To search, there is a protocol. It has to follow some language. And in a very good approximation, they actually follow these protocols. They go searching randomly at where the places are, and then they identify this has some prominent one, and then they get an output. So there is a very high chances of not going and finding the place what you want, and then you still get a reasonable result. But what quantum mechanics says is that you can actually be at two places simultaneously. So that's what quantum mechanics is trying to tell us, right? But atoms can be in two different states simultaneously. I can have light in superposition, like a horizontal or vertical polarization, what we talked about it. We have a circular polarization. which is a superposition of both the states. So now you can also have light or spin of electrons being in superposition. What that says is that if I have multiple electrons and then put them in some complicated interaction situation, then you can simultaneously explore all the possible options for you. That's what we call as superposition and interference. Both of them happens because there is something which goes from here to here, and then there is something which comes from here. So same particle or like same person is getting interfered, and then there is some probability of finding something what you want. It's like making your search better. So people have developed quantum algorithms which says if I use quantum physics to do search, it can do quadratically faster. And that's one of the famous algorithm in quantum sciences or quantum technology, what we call quantum computing. It's called Grover's algorithm. So they showed that if I am using quantum systems, I can search quadratically faster than classical one. So that was a very big result. So then people said, yes, then we have to start using quantum mechanics as our fundamental component to build computers rather than going on with the classical mechanics based technologies. So that's why we are all driven towards us. There is one more very important feature which nature has given us as a gift, which we call as entanglement, which a lot of people find. Even Einstein for decades was very confused, and he said he can't believe that this can happen in nature, and he was trying to come up with some theories to counter it. But it has survived, and today people have been doing, in our labs we generate such kind of states. What it says is that I can generate some entangled state. It's called as entanglement. So I can send one to, keep in one in Bangalore and send another one to some other place, right? In some unique way, I create a joint pair. We can call them as cousins. So one is sent to some place and the other is kept with me. But I can know what happens to the other one who is hundreds of kilometers instantaneously, right? So I will redefine it, but then now I will give another counter example. How much time do we need to communicate between Bangalore to Chennai? If I have to exchange, there is a fraction of second, but we can metric in the sense we can estimate how do we estimate? How do we estimate the time required to communicate to any other person? Or how are they communicated? Huh? How are they communicated? Huh? Sorry? Time. Timer? No, timers are, but the signal has, some information has to be communicated, right? So something is there which is going. What is it? What is the source for it? If you go back my first slide, I said there are discoveries, right? So there is electromagnetic waves in some for the other form, right? Either it is your wireless telephone, mobile phones, or it's connections, or it's an optical fiber connecting India to US over the sea. Whatever it is, there is an electromagnetic signal which is going from point A to B. Only from that you have been established. Or it is going to a satellite and satellite is connecting you. So what is the limit for that? What defines the speed of it? Speed of light, right? Speed of light is 3 into 10 to the power of 8 meters per second. So it means that you can't communicate anything faster than that. But entanglement actually allows you to do faster than that. What it says that you can actually create two of them. I can share it between two cities and they can have, and the moment I get to know what is the information of one, instantaneously I get to know information on the other one. So now this was considered as spooky action, weird behavior, all of those things, but over and over, many experiments have demonstrated that this is true and we can do that in lab, right? People have communicated in the sense, I've done this experiment for thousands of kilometers. So what does this help in communication, secure communication? If signal is sent from A to B, which means that you need a channel for it to go. It can be a space or it can be an optical fiber. Somebody can tap that. Somebody can steal your information. Now, if you don't even have a channel and instantaneously you can have information exchange, then your information is secured. So most of the countries, security agencies think this is the most important thing. And if you see why quantum is in the buzz, this was also one of the biggest concern by all the nations. If you have to communicate securely without anybody hacking, then we need to exploit quantum physics to have a secured communication. So this is something which, this is small animation. It says if I send a light, there is some unique way we can create. you can have a unique material where these cousins can be created. So you can send them at to 2 points. Okay, sorry, I have. Okay, so what it does is that there is some correlation, what we call exchange. So one can be H, horizontal polarization, then instantaneously the other will be V. If the other one is V, the other one will be H. So now when we talk about 0 and 1s, that is our information, right? I can always map my H and V to 0. Then the moment I get H here, then I can say I've got 1, then the other one will be V, yes, got 0. So now I can say 0 means I can flip, I can get back 1. So zeros and 1 sequence can be instantaneously recovered. So that's what is a big advantage which we get from entanglement. People got Nobel, I think 2 years back, the Nobel Prize was given for demonstrating these experiments, and they did the work in 1980s, but the Nobel Prize was given last 2 years back. So if you see, over last 80 years, a lot of science has happened to understand and development, and from 1980s onwards, people have started doing experiments in lab, and over last few years, I should say, it's only been very few years, where people have started building technologies associated with it. Now, what are the three principles which the three principles which I want to highlight here is superposition, because that allows the particle to be at two places simultaneously. And then there is an interference, which means that like a wave, they can interfere. So there is a particle behavior and wave behavior. Advantage of both of them are combined together. And there is entanglement, which I showed in my last slide. So these three we call as a key fundamental features which we have got from understanding nature at atomic level, or what we call subatomic level. So how do we control them and then leverage them? And that is where whole quantum technology is heading towards. So over last few years, looking at the opportunities, India launched National Quantum Mission 2 years back, and then we want, like any other countries. So whole idea was that, so there are 9 missions which Indian government launched, like any other part of the world. In fact, we were a bit behind. So other countries had launched their missions a bit earlier. In that, quantum technology is one of them. And there's a grant which was approved over last 8 years. It's not only to support academia or research. It's to support the startups. It's the big industries, so that you come up with the technology. So the way it is now is that we have 4 verticals. So it means that it is not about building one device. It is not about building one particular application. So it's about building multiple devices which has wide applications. Everywhere you are thinking about technology, you can bring in quantum into that, and then see how it can help to change. So the way it has been, and at least India's National Quantum Mission has been divided, we have 4 verticals. We say how I can leverage those 3 basic principles which I tried to describe in my earlier slides to do a fast and better computation, and how I can use them to have a most efficient and secure communication. So that's communication. And then how I can build a very sensitive and good materials. There are many examples. Simple examples are solar cells, which I can give. They are not highly efficient. So they are like few percentage is what we can leverage out of it. Like 20% is the best we can get to convert energy. So can I understand at atomic level and build a highly efficient materials to have better solar cells, which means that our energy problems can be solved to a very great extent. If I have a solar cells which are 80% efficient, then our energy problems can be solved to a very great extent. So that's one example, but can I have a more efficient materials for medical purposes, all of those things. So quantum materials and devices, another vertical. And then there is sensing and metrology. So when we are talking about sensing and metrology, we are trying to say magnetometers, or you're trying to look at interferometers and various other things. They have certain sensitivity, like gravity, even earthquakes. So these are all like sensors. Sensors detect what can happen or not, but can we say earthquake is going to happen at so and so with high precision? There are some devices which people have built, seismometers are there, but seismography is one of the topic which we are trying to look at. But can we have a predictability and get better by understanding them at the quantum level? So there are these 4 verticals which National Quantum Mission has launched. Computing is at IISc. We are looking after quantum computing for the whole nation. So there is one hub which has been established. Communication is at IIT Madras. and materials and devices at IIT Delhi, and then sensing and materials is at IIT Mumbai. So these are the four verticals which has been into. So there has been a lot of collaborative work which people are working on to build. So there is so many institutions, 42 or 43 institutions, and involving all the states which are developing technologies and devices. So the idea of the mission, the mandates of the hubs, like for example, IISc's Quantum Computing Hub, which we are looking after, the mandate for us is to, one, we have to do research in our lab, build devices, that's there. Next one is to support startups and industry partnership, and then to even create, conduct R&D at sub-teams level. And this is one of the most important things, because I can talk about technology, I can give, but we need people who understand little bit of science and then start building technology. So we need to look at the core, increasing core research base in the country so that we build technologies. So today we are dependent on technologies built on various other countries we import. Like China might make something, Korea would make something, we buy them. Why is it? Because they are cheaper. Why is it cheaper? Because they were ahead of time. It was expensive initially before for them, but when they started doing mass production, it became cheaper. Indians can build today, but what happens is if they're starting, some startup is trying to build some devices, there may not be a big market and the cost will be very high. Then people will think, oh, I can import it, it's cheaper. And that's how we have killed our manufacturing, to some extent. And now can we, undo those things when the quantum technology era? Can we start building it at the early stage so that India can get an edge? So that's how we are trying to look at this problem. Most of the ministries have got together and trying to see how we can build an ecosystem. So there is a few startups which National Quantum Mission has already supported. One is under quantum this is communication, QNU, and one is for the computing. And there are, why I have listed many of them is that you don't even have to even think of only quantum devices. There is a lot of support system which has to be built around, and they all need small components. And can people build small components which are needed to put quantum computers together? So can they build small components which we can put communications devices together? When I say communication device, which means that can I have communication between 2 points, like I said, entanglement, right? So you don't need any channel, can you communicate securely? So these are the things which some of these startups which has been selected in the first round, but there's been a continuous call to look at it. And the awareness program's idea is that to enhance awareness in quantum technology among students, researchers, industrials, professionals, and policymakers. At least some part I'm trying to address here, where students are here and then some industry partners are there. And then we need to build capacity. That's the most important part. And then how we can come up with a policy so that the things can be built in the country, we can use it effectively for our applications, right? There is last year, I think under the National Quantum Mission, so there has been a curriculum which has been developed. Most of the researchers, most of us, we were working on the field, contributed for it, so that there is already course which has been floated for both BTech minor and MTech courses on quantum technologies, where curriculum has been designed so that we are building next stage technologists in the country. This has been started. And there has been a continuous call among all the four hubs which I told. There's computing, sensing, and materials. And you can see their web pages, and then you can look at whether you can submit your proposals for it and then get support for the startup. There's been quite generous push from the government for it. So there has also been, one of the things which lacked in the country was fabrication facilities. Most of the time, today we are talking about semiconducting fab facilities. We are very late. A lot of countries had established long back, but quantum also needs certain fabrication. If I have to build something at atomic scale, I need to have a very good facilities. So there has been central facilities which are coming up at IISc Bangalore and IIT Mumbai, and also there are other parts which are coming. And these central facilities are not meant only for academic institutions. There can be an industry, startups who can all submit their request and they can use them. That's why they're called as central facilities. So it's getting a bit more easier to fabricate few things and come up with ideas. So these things have started. The funds have been allotted, and over next 1 year time we'll have facilities established in the country. So various ministries. So if you start looking at the details, there has been ecosystem which has been systematically being built to start looking at how we can involve all stakeholders. It can be schools, colleges, ministries, everything. So the roadmaps have been set into. So what I meant by quantum computer and where we need a lot of small scale industries to pitch in is not just to build this chip. So this is only a chip for quantum computer, small number of qubits, which I think this is Google's, IBM has built, and some of them are also even built in Indian research labs. This is a small chip, but then the whole system requires a lot of electronics, wiring, and various other things. There's another example for one more quantum computer. It's also a quantum computer. That's how it looks like now. Next 10 years later on, it might look like this. Uses photons, light to do computation. Now, if you look at, there is a lot of components which are not talking about, it's not about atomic scale. These are a good mirrors. These are good mirror holders. These are very high quality, high precision, control systems. So control systems, I mean, just lens holders also. If I make small rotations, they will only have some millimeter shifts or something. High precision control optics. So most of us in our labs, we import them. We import from 2 to the different countries. But can these things be manufactured in India to supply for the quantum technology revolution which is happening? For example, this is one example of one of the quantum computers, which is an IBM, we can say. A small chip, quantum chip sits here. It makes only 2% of the device or even less than that. But the rest of the 98 is all the support system, which can involve building a cryogenic system, a flexi cables, or it can be, if I'm looking at photonic quantum computing, it can be a light source, or it can be detectors. So all of those things may not need you to know even quantum computing or quantum mechanics, but these are the systems which are helping to build a quantum devices. So there are hundreds of them, and there are, in fact, why the government also is interested under National Quantum Mission. There has been a lot of initiative to support building these small components. If somebody comes up with, I'm building a small flexi cables which are highly efficient without any resistance loss and all, then they will be useful. Right? You don't have to look at, just pick up one small component, and if you start manufacturing them, in fact, the world may be procuring from you. So these are the way we are trying to initiate to build components in the country. So there are many examples. In fact, we also try. So that's how, when I said I can see quantum computers of current era like this. This was in 1930s. First classical computers were built in University of Berkeley. It was like 2-story building. It just did a simple calculation. But over years, they got converted into a very powerful, small, compact devices. That's how quantum technology is also going to do for quantum computers. This is small computer in our lab. This doesn't even look like a computer, but yes, it is a 6-qubit computer in our lab. And it's a small other 2-qubit computer which we have. But these all look bulky right now. But over time, they all will get compact, and then there's a lot of supporting systems to be built around it. So there are multiple devices which we can talk about encrypting, decrypting information. So we can generate keys, which has become very practical. I was mentioning about exchanging keys between A and B, right? So today we get your keys from some computer devices, and there's a program written for that. And if somebody knows what is the program written for it, they will have an information of those keys. Then they are not secure. So you only trust the service provider, how much reliable it is. Like, for example, I trust a brand. I go there and I say, this brand has less failure, I will trust them. And somewhere you go for your food, you say, okay, the quality is good, you trust, and you continue with it. This is just the trust. But can I say I don't have to trust, can let nature decide? And that's how we generate keys using quantum devices. So you don't have to rely on any program or something. There's atom or there are photon which gives key. And we can do some encryption of it, which nobody can hack, because the keys are, nobody can even crack the keys. Entanglement, when I said there is entanglement between two, the keys goes to one point, and then there's one more set of keys goes to other point. Only when they match, you can decrypt. And entanglement is decided by nature and not some programming. So this is something which you could demonstrate with a smaller number of qubits. You don't have to build a big computer. Smaller computers have some applications. And these devices have been used. Like, why we are not very late in time is that if you look at this, another small 2-qubit computer which was built by Cambridge Quantum Computing, and what we build in India is much more faster, with higher rate compared to them. So which means that just, we are all close by. We may not lose the race if you are trying to go fast and then catch up with them. So these are some other examples which has been built right now in Indian research labs. In fact, this has been built in IISc's lab, one of my colleagues, Vibhor Singh's, where I said the supercomputing or like superconducting qubits call needs a lot of fine materials to build or like to connect the qubits and to control electronics, all of them. So they are fabricated and build them all in their labs. When we have central facilities, they can be built in a much more efficient way. Small scale industries and small startups can actually think of building them all and supplying, and we don't have to rely on just one or two suppliers from outside. So there are prototypes which have been built in research labs. The industries can take over of them and then scale up. So there are control electronics. This was again built in India in IISc, one of my colleagues' research lab, where you need to control these quantum devices. So which means you need to have some electronics which drives them a bit more efficient than the electronics which are needed for regular systems, but they can be done. People didn't think about building such kind of precise electronics because there was no need for it, but now there is a need and they can build. So these are some of the fields where people can start building, just getting motivated from what has been done in academia, because academia's role is not to take to the market or build it a large scale. It is the industries who can pick up from there and then make it much more customizable and make it much more directly user friendly. So I think I'm probably out of time, so I'll just give few more examples which just happened. What surprised us was there has been lot of laser usage in the country. We buy them, and that's always been a big drawback. But right now what has happened is there was some research group in IIT Delhi. We started building diode. This is from there. One of my colleagues said going to build lasers. Now the problem is that these lasers which we are procuring from outside of the country have been tested for many years, and trust is there, we buy. So but they said they are going to build, but where is the market? Then we said, okay, we within academia will try to test and improvise, and these are the lasers which they have built, which we are going to use for building quantum computers and various other applications. But there are no big startups or industries which are building many things from scratch. So all these examples are like something which have come up in India just in last 1.5 years. I know them all. I know all this personal PIs, what they call. This from IIT Delhi, which they have built the first cryoflexi cables. Like, there are cables which can connect one part of the device to another one, and they have come up with it, and they have spin up from IIT Mumbai. And it's control electronics, again, it's one of the other inter-university center for accelerator, where they were building it for something else. They realized they are useful for quantum computers. They have built control electronic system for many for different kind of hardwares. This is again a superconducting nanowire detectors. Another young graduate, he did his PhD from abroad and he wanted to come back to India, and he has set up, and next 1 month or something, they are building these high precision detectors. Now there are only 3-4 companies which are building them in the world, and it's good that something started in it, the 5th or 6th company. So there are hundreds of small things which one can look at and start building, and there will be a lot of rooms for its improvisation over next few years. Right? So I think I will. There are other examples of how we can leverage on it. There are many of this. These are like the devices which we are trying to build on our lab, and then do some trials for sensing and communication purposes. These are beams which we send to align the light so that we can send photons to those paths. So you need to align. Photons are very small, in the sense one after another you can't detect them if they are very low in number. But I need to have a line of sight. So first you align with the normal lasers, and then you send photons, do communications. What I said, we could establish some direct secret communications and those things. The experiments can be done, but these are not prototyped. These are not compact devices. They all can be converted. The science have been established, so now the technologies can be taken forward by industries next time. So the whole idea, what we as a nation should look forward to here is to build a quantum workforce for future. Future, I'm not talking about 1, 2, 3 months. It's like next 20 years, 30 years. It's not that we are forcing, it is there are resources we have to leverage and build, or else will again be the end users of something which has been developed by somebody. So I think it's the last slide, I guess. Yes, thank you. And I can just take few questions if there's. Yeah.